Hello everyone. In this video, I will be talking about RDKit. Before I go into the coding aspect of it, I want to talk briefly about the importance of RDKit in chemoinformatics. RDKit is a powerful chemoinformatics toolkit in Python that provides a wide range of functionalities for working with chemical informatics, including molecular structure handling, molecular descriptor calculation, chemoinformatics analysis, and more. It can aid in molecular structure handling. RDKit allows you to read and write molecular structures in various formats, including SDF, SMILES, and others. In fact, you can visualize molecular structures using RDKit to get a better understanding of the chemical compounds you are working with. RDKit also allows you to perform fragmentation and decomposition of molecules, which can be useful for understanding the structural hierarchy of complex compounds. It offers functionalities for substructure searching, similarity searching, and molecular clustering. These tools are essential for comparing and analyzing large sets of molecular structures. RDKit provides tools for calculating various molecular descriptors and fingerprints, which are numerical representation of chemical structures. This can be useful for quantitative structure-activity relationship studies and machine learning applications. RDKit also supports the handling of chemical reactions, making it useful for synthetic chemistry and reaction informatics. You can analyze reaction outcomes, reaction mechanisms, and retrosynthetic analysis. Now the very first question is that if we have a bunch of molecules, how are we gonna be presenting these to the computers? So there are various ways you can do it. One of the simplest ways is SMILES representation. And what is SMILES representation of molecules? SMILES stands for Simplified Molecular Input Line Entry System. It is a notation that allows a user to represent a chemical structure in a way that can be used by the computers. So SMILES is basically a text-based representation of chemical structures and is widely used in chemoinformatics and computational chemistry. The basic idea behind SMILES is to represent a molecule as a line of text that encodes its structure. In SMILES notation, atoms are generally represented by their atomic symbols. For example, C for carbon, O for oxygen. Bonds are represented by specific characters. Example, dash for a single bond, equal to sign for a double bond, and hash for a triple bond. Parentheses are used to indicate branches or groups. Rings are represented by numbers. So the first step is converting these molecular structures into SMILES representation of molecules so that can be input into the computer system for it to read and analyze. You can convert these molecules into SMILES strings using commonly used software such as ChemDraw, and also there are online tools available which can aid you in converting these structures to SMILES strings. Now let me just take you to the Google Colab notebook and show you how you can analyze these type of molecules in RDKit. I'm gonna start off by installing RDKit using pip install RDKit. For the purpose of reproducing this code, I highly recommend you to install the same version that I'm installing. So let's go ahead and do that. Next, I am importing important modules from RDKit as well as some other libraries such as pandas and numpy, which would aid us in reading and writing Excel files. Let's go ahead and run this. Next, for this tutorial, I am using this Excel file which contains names and SMILES strings of around 50 nitrogen containing molecules. I am reading this file with the help of pandas. Let's just read this and have a look at the first 5 data points. So you can see we have 2 columns here. One is the name of the molecules and the other column contains the SMILES strings of these molecules. You can get more information about this dataset using .info command. As you can see here, we have 2 columns and 50 values, and we don't have any missing values. Now let's just see how we can use RDKit for reading, drawing and writing molecules. The first and foremost step in RDKit is converting these SMILES strings into molecular objects. Generating molecular objects in RDKit is a fundamental aspect of chemoinformatics and computational chemistry. Molecular objects, often represented as instances of the mole class in RDKit, serve as data structures that encapsulate the information about the chemical structure of a molecule. Molecular objects store information about atoms, bonds, and other structural features of a molecule. This representation allows for easy manipulation and analysis of chemical structures in a programmatic way. Now let us just start by converting a single smile string into a molecular object. So what I have done here is I have copied the very first smile strings in the molecule and pasted it here. Now we are going to be using this chem module, which has this mole from smiles function, which takes in smile strings as an argument, and we are going to be storing this molecular object in a variable called mole. Let's run this command and let's print out our mole object. So this is how our molecular object looks like. This is just a data structure which has all the information about this molecule. Now if you want to draw this or visualize this molecule, you can use draw.mole to image command here, which takes argument as the molecular objects. So let's run this command and have a look at our molecule. So you can see this is the very first molecule which we have over here, 1,4-mylpiperidine. Now we're gonna go ahead and save this molecule as a PNG image. For that I am using this draw module and mole to file function, which takes in argument as our molecular object which we have created over here, and we have to input the name of the file in which we wanna store this image. So let's run this. Now over here you can see that we have an image called mole.png. Let's download it and open it. So you can see we have a PNG image of this molecule, and we can just use this image as per our requirement. Now the next step is, let's say we want to generate these molecular objects for the whole data set. Let me just print out the data frame. So what I'm gonna do here is I'm gonna be creating an empty list called mole_list, and I'm gonna be looping through each smile string. So in the first instant, this chem.mole from smile will take input as the smile string and convert it into a molecular object, and we are gonna be appending this molecular object into this empty list. And at the end of loop we will have 50 molecular objects in this list here, because we have 15 smile strings. And what we are going to do then is we are going to be converting this list into a data frame along with the column name as mole, and we are going to be concatenating it to our original data set, which has names and smiles. So let's go ahead and do that and have a look at our first 5 data points. Now you can see we have now 3 columns. First one is name, second one is smiles, and the third one is the molecular objects that we have just created. Now you can visualize these molecule objects with the help of moles to grid image, which would print out these molecular structures in a grid format. The first argument is pandas series here. I am just printing out the first 16 molecules. The second parameter here is moles per row. So basically we have given the value of 4. That means we want to print 4 molecular structures in a single row. This is the image size. You can increase or decrease it as per your requirement. And this is the legend. I also want to print out the names of these molecules just below the structure of the image, and that's why I'm just using a list comprehension here. So let's run this command and visualize our image. So you can see the molecular structures of these 16 images have been printed out in the form of a grid along with their names. There is one more thing I wanna point out, that just in case you wanna add hydrogens to these molecules, because right now you don't really see any hydrogens, and sometime you want to add hydrogens, because for calculating 3D descriptors generally it's recommended that you have hydrogens attached in your molecular object. So for that, all you have to do is in this for loop just use this chem.addHs function here, which would take in the molecular objects that we have just created in the code above. So before I rerun this command, let me just read the file again here and override the df variable. Otherwise it will create another column with the same name called mole. So let me run this and see our output. So now we have a mole column attached to this data frame, and let's visualize this again in the form of grid. So now you can see that we have hydrogens attached to these molecular structures. Now let's say if you want to save this image, you can use this piece of code here, and let me just break down this code for you. This part opens a file name called image.png in a binary write mode. This WB mode is used when working with binary files like images. Now if the file does not exist, like in our case this file doesn't really exist, it will be created, and if it does exist, it will be truncated to 0 length before writing. Now this part of the command, this part writes the binary data contained in the image.data. So this is our data is stored in this image. So basically this command here is going to write this data into this image. Now let's move on. Apart from running for loop, there is an easy way to do this as well. We can use this pandas tool module, which has this function add molecule column to frame. This takes in input as smile strings from this data frame and creates another column called mole, like the one we just generated, and which has molecular objects in it. So let me just run this command and see our data set. Now the data set looks similar, but in this case the hydrogens would be missing. So let me just again print out the molecular structures in a grid format and see our image. Now you can see here this mole column is overwritten and we have these structures without hydrogen. Now this was one of the way by which you can read the molecular structures using smiles, right? Now there is another way you can do it. You can use .sdf files, and let me just give you a brief description about these .sdf files before we move ahead. SDF stands for Structural Data File, and it is a file format commonly used in chemoinformatics to store and exchange chemical structure information. The SDF file format is flexible and can contain data for more than one chemical compounds. It is often used to store information about molecular structures, including atom types, bond types, 2D and 3D coordinates, and additional data files such as molecular properties. Now let me just give you a quick example. This is an dimethyl formamide, and this is the SDF file of this molecule. Now here is just a brief overview of how SDF file looks like. We have basically three main blocks. The first one is a header block. The file typically begins with a header block that contains general information about the file. So this is the header here, which has some form of ID or even names of these molecules. The second one is C tab, or connection table block. This is the main section of the SDF file. So this over here is the connection table. Here the chemical structure information is stored. Each compound has its own C tab block, which includes details about atoms, bonds, and possibly substructure information. So the next one is data block. SDF file can also include data blocks where additional information about each compound is stored. This information can include properties such as molecular weight, boiling point, melting point, and other relevant data. And this is the file that I have downloaded from PubChem, and as you can see, it has some descriptors like PubChem hydrogen bond acceptors, PubChem hydrogen bond donors, rotatable bonds, and stuff like that. So this constitute a data block. Now this is the SDF file for a single molecule. A single SDF file can contain multiple molecules as well, and I'm gonna be showing you that in this tutorial. So let me just print out our data set real quick. And if you're wondering where can we get these .sdf files of molecules, so what I'm doing here is just randomly grabbing let's say this molecule over here, and I'm going to PubChem repository. Here in the search tab, I'm just pasting this smile strings, and I'm gonna be searching for this molecule. So you can see we have information here. This is an dimethyl propionamide. What I'm gonna do is I'm gonna go to the download section here, and I'm just gonna download the SDF file by just clicking on this button here. You can either download this SDF file containing 2D or 3D coordinates. I'm just sticking to 2D coordinates for now. So let's just click on this button, and this file will be downloaded into your computer. So what I'm gonna do real quick is rename this file as sample.sdf, and I'm gonna be importing this file to my Google Colab notebook. So I have the sample.sdf file in my Google Colab notebook. Now what I'm gonna do is I'm gonna be using this pandas tools module, and I'm gonna be using this load sdf function here, which takes input as the name of the sdf file, and this smiles name parameter would make a column called smiles with smile strings of this molecule, and thus this mole call name parameter would make another column called molecule, which would have the molecular object of this molecule in a data frame. So let's run this and let's have a look at our data frame. Now since I showed you this file contains data block which contains some additional information, so that is also printed here. For example, hydrogen bond donors, we have 0, rotatable bonds 1, and so on. But the main thing here I want to show you that we have the smile strings in here, and along with the molecular object, this one over here. Now you can also just grab this column, and the first index would be this molecular object. So let me just print it right over here. So you can see this is our molecular object that we have created over here. Just in case if there are multiple molecules in your SDF file, then we can use a SDF supplier for reading these files. Now we have this approved_drugs.sdf file on the GitHub page of RDKit. So what I'm gonna do is just download this SDF file using wget command. So it has finished downloading. So you can see over here we have approved_drugs.sdf file. Now let me give you a quick glimpse of how this .sdf file looks like. Now you can see here, this is the header block. It has some ID in it. This is the C tab block, which has the connections of the different atoms and information about bonds. And this is the data block here, which has some additional information. And after the data block ends, right over here, another molecule starts. So this is the header block of the second molecule, and C tab of second molecule right here. And then in the end we have a data block. So this goes on, and in this file we have around more than 1200 molecules. So let's just go back to the Google Colab notebook and read this file. So what I'm gonna be using is a chem module and st_mol supplier, which will take argument as the name of the file approved_drugs.sdf, which contain information about multiple molecules. And what I'm gonna be doing here is that I'm gonna be storing this in st_mol. So let's just run the first code over here, and what I'm gonna do here is I'm just gonna see what this st_mol looks like. So st_mol is an object, and this is not just a single object, it's a list of objects. So let me just convert it into a list and see what we have in here. So now you can see we have a list of large number of objects, and each of this object is kind of a molecular object. And what we can do is we can iterate through each mole object here and print out the images. So let's basically right now I am just dealing with 5 molecules. I just don't want to overwhelm my computer with all this data here, so I'm just using the first 5 molecular objects, and I'm gonna be printing their images out. So let's just have a look at the output. So these are the first 5 molecular structures in our approved_drugs. Now if you want to have a look at the length, I am running a length function on it. So let's see how many molecules are there. So it has information about 1284 molecules. Now again, let's just visualize these molecules in a grid format. So I'm just visualizing the first 16 molecules. So these are the first 16 molecules that we have in our approved underscore drugs file. Now let us say you have the molecular objects and you wanna write these molecular objects in the form of smile strings. We can do that in RDKit. Let me just print out our data frame. So we have this data frame here. Let me just grab the first molecular object and store it in a variable called mol underscore 0. Let's print out this molecule object, and this is one for milpiperidine here. Now let's say I want to convert this molecular object into smile string. So what I can do is use this chem module and mol to smiles function, which takes in the molecular object as the argument. So let's run this. So we have the smile strings for this molecule. Now this is particularly useful when we have like 2D or 3D coordinates of compounds in, let's say, in SDF file format. So like I showed you, we can just read this file containing large number of molecules using SD multiplier, and this SD mol contains molecular objects of these molecules. So what I'm gonna do here is that I'm gonna create an empty list here, drugs underscore smiles, and I'm gonna iterate through each object in this SD mol variable. And I'm going to be converting these molecular objects to smiles using dot mol to smiles, and in the end I'm going to be appending these smiles to this empty list. So at the end of this for loop we will have smile strings of 1284 molecules, but I am just printing the first 10 smiles. So let's do that. So you can see we have the smile strings of these molecules stored as a list. Moving on to our next topic, you can also use RDKit to generate 2D and 3D geometries from their smile strings. So let's again have a look at our data frame. So let us just say we want to compute the 2D coordinates of this molecule over here. So again, the first step is generating its molecular objects. Now we have already done that, but let me just do it again here and store it as a variable called m. I'm using the same old dot mol from smiles command, which would convert this smile string into molecular object. And this I am just naming the file as mol-2d. Now this is the function here which would compute the 2D coordinates of this molecular objects. So let me just run this, and it has given us an output as 0. So that means this function here was successful in generating 2D coordinates. Now if you want to visualize these 2D coordinates, what you have to do is use this mol to mol block function here, and put the input as the molecular object that we have used in here. So let's print this out. So you can see these 2D coordinates. I think this is very familiar. We have seen these type of coordinates in .sdf file. Now let's say you want to store these coordinates as SDF file or even .mol file. So what you have to do is just use this file is equal to open, which would again open this SDF file. If it doesn't exist, it would create this mol-2d.sdf file, and it will just write the data from this mol block. So let me just run this command, and you can see over here we have this mol-2d.sdf file. Now let's just download it, and I'm gonna be showing you in ChemDraw. So now you can see in the ChemDraw this mol-2d.sdf file has the 2D structure of this molecule. Next, what if you want to generate 3D coordinates? And that's really important, especially when you want to generate 3D descriptors. So again, the first step is generating a molecular object from their smiles. Next, I'm just naming this molecule as mol-3D. Next, I'm adding hydrogens to this molecule using chem.addhs command, which would take in argument as the molecular object that we have just generated. And in the end, in order to generate 3D coordinate, this is the command here, allchem.embed molecule, which would take the molecular object which we have just generated after adding hydrogens. So let's run this, and again we have got the output as 0. That means it was successful in generating the 3D coordinates. Now in order to visualize these 3D coordinates, I am using the same command, .mol to mol block, and you can see the 3D coordinates of the molecule in here. Now after generating the 3D coordinates, you can also see the difference in their structures in here. So let me just print out these molecules. So let me just go above here. Now you can see here when we generated the 2D coordinates, we stored this in a molecular object called M, and for 3D we have the molecular object M2. So let me print out both M and M2 and show you the difference. This is an dimethyl propionamide, and this is the 2D structure, and this is the 3D structure, and you can very well see that it has the 3D tinge to it. Next, again, if you want to save this, it's the same procedure. I'm saving this file as mol-3d.mol. You can also save this as .sdf. It's pretty much the same. After I've run this file, it has been stored over here, which I'm gonna be downloading it on my computer, and I'm gonna be showing you in my camera. So this is the this is how this molecule looks like in camera, and you can see it has a 3D geometry to it. Next, you can also optimize these molecules using molecular force field. You can use this module allchem and mmff optimize molecule conformation, which would take in the 3D structure of this molecule. Now this is M2 is the 3D structure, right? Now let us just say you're using the 2D structure, which was M here. Let me just run this and see what output we get. So you can see it is throwing us an error, bad conformer ID. That's because it does not has the 3D coordinates for optimizing. Now let me just change it to M2, which is the 3D structure, and run it again. So you can see it has run, and let me see the output. So this 0 tells us that it has been successfully run, and this is the value of the energy of the molecule. Now with the help of RDKit, you can also get atom-centric properties of the molecules. This time, let's just have a look at the bottom 5 data points of the dataset. So these are the bottom 5 data points. Now let's just convert this dimethyl ethyl urea into a molecular object. So we have the molecular object created from the smile strings. Next, what I'm gonna do is I'm gonna use getAtoms function on this molecular object, and I'm gonna be storing as a list in a variable called atom_list. Let's run this and print our atom_list variable. So you can see this is again an atom object here. Now it has information stored in it of all the atoms in this molecule. Now if you want to grab some information on it, you need to call some function on it. For example, let's say I'm interested in knowing the just say the very first index, and I want to grab the symbol of it. So what I'm gonna be doing here is I'm gonna be grabbing the 0 index here, and I'm using this get symbol command for getting the symbol of the atom at index position 0. So so that atom is oxygen here. Let's go ahead and see what's at atom index 1. So it is carbon. I'm guessing at index position 2 we will have nitrogen. Let's check. So you can easily get the symbols of the atoms in this manner. There's another way. You can use call this atom with index id function on it followed by get symbol. It will give you the same answer. So at index position 1 we have carbon. At index position 2, let's see, we have nitrogen here. You can also, apart from getting symbols, you can get the atomic number as well, and there are many other things which you can get. Now we know at atom index position 2 we have nitrogen, so let's just get the atomic number of it. So it has printed out the atomic number of nitrogen. You can also get information about the bonds. What you have to do here is you have to mention for what bond you want to get the information about. So what I'm doing is using this get bond between atoms command, which takes in argument as the indices of the atoms. So I want to know what type of bond is present between atom index number 0 and atom index number 1, which is here 0 and 1, oxygen and carbon, and I want to know the bond type. So let's run this and see the output. So it is a double bond here, this carbonyl bond. Now Let's say I want to grab the information of all the atoms. Let's say I want to grab their index ID, symbols, as well as atomic number. So what I'm going to do is I'm going to run a for loop through each atom. So let's run this and see the output. So you can see we have the index positions, their symbols, and atomic number. You can get other information as well, like their hybridization. So you can use get hybridization function. So here we have the information of atom index, symbols, and hybridization. Next, I want to talk about how you can highlight molecules in RDKit. Atoms in a molecule can be highlighted by drawing a colored solid or open circle around them, and bonds likewise can have a colored outline applied. An obvious use is to show atoms and bonds that have matched a substructure query. So basically, it can be used for substructure searches. Now, let me just randomly grab 35th molecule, which is at 34th index number. This is N-diethyl acetamide. Now let us just suppose that I wanna color this amide bond here. For that I need to grab this pattern here, and for that I'm using chem.mol from smarts command, and I am giving an argument of this amide bond here. Now till now we have worked with smiles. This smarts is just new to us in this lecture, so let me just give you a brief outline of what smarts notations are. Smarts or smiles arbitrary target specification is an extension of the smiles, and while smiles is primarily used to represent individual chemical structures, smarts is designed to represent patterns or substructures within chemical structures. Smarts is particularly useful in the context of substructure searching, where the goal is to identify molecules containing a specific structural motif. So let me just show you, what's the actual difference between them. Here, smiles describes the entire molecular structure, including atoms and bonds, whereas in smarts you can use wildcards and logical operators to represent variable atoms or bonds within a pattern. In smiles typically represent specific atoms and bonds, for example carbon, C for carbon, and dash for a single bond, whereas in smarts you can use wildcards such as star to represent any atom or bond. Logical operators like and, or not can be used to create complex patterns. Now let me explain this with the help of few examples. In this example over here, both smiles and smarts represent an aromatic benzene ring. So basically, smiles and smarts can have the same notation as well. In here, smiles is used to describe a specific alkyl chain, whereas smarts can represent any linear chain of 3 carbon atoms connected by a single bond. Regarding wildcards in smart, the smarts pattern over here represent any carbon atom followed by 2 arbitrary atoms. So basically it's not specific, you just need to have 1 carbon, and you can have 2 arbitrary atoms with this type of notation. Logical operators in smarts, so you can have this or and operator. So this is an or operator here. This smarts pattern describes either a carboxylic group or a simple alkyl chain. So in here, this smarts pattern represents any carbon, nitrogen, or oxygen atom except for those with 0 implicit hydrogen atoms. So I hope you have got a brief idea how smarts differ from smiles. Smiles are basically holistic representation of a molecule, whereas smarts represent generally substructures or patterns. So in here, for highlighting this molecule, I am grabbing this smarts pattern of this amide bond here, and I am storing this in a variable called pat. Now next, I am using mol.get substructure match, and I am putting in an argument of this pattern here. So what it will do is it will just grab the indices of the atoms in this molecule which has this pattern. So let me just comment this one out and show you how this hit underscore adds looks like. So in the output we have 2, 1 and 7 that represents the indices of the atoms in this molecule in context of this pattern. Let me explain you more clearly. Up here we grabbed the atom-centric properties of the molecule. So what I'm gonna do here is I'm gonna be copying this command. I'm gonna paste it here. What I'm gonna do is I'm gonna get the atoms in this molecule here. So we are using mole variable. Now I'm gonna be getting the atom index symbol. We don't really need the atomic number, so I'm gonna be deleting that. Let's run this. So we can see here at number 2 index we have nitrogen. So this is the nitrogen of the amide bond. At index position 1 we have the carbon, this carbon over here, and at index position 7 we have this oxygen or of this molecule, and this is the carbonyl oxygen. So basically hit underscore adds has grabbed the indices of this pattern over here. Now I'm just gonna delete this as we don't really need this anymore, and I'm gonna just uncomment this. So let me just run this. This D here is basically will create an SVG image, and in the next piece of code here we are using this prepare and draw molecule function, which would take in arguments as D, which is the SVG image, molecule which we want to color, and the index position of the pattern. So let's run this. Now I'm gonna be printing the molecular structure of this molecule. So now you can see this amide bond has been colored in this molecule here. Now let us say you have a data set which has lots of molecules in it. Like in our case, we have around 50 molecules. Let's say you just wanna color this pattern in all of these molecules. So all you have to do is just add a for loop here. Rest of the commands are same. So let me run this real quick and have a look at our data set. In the output of the dataset, you can see we have name, smiles, as well as the molecular objects or graphs, and we can see this amide portion is colored in all of these molecules. This is nitrile, so they don't really have any amide bond, so we don't really see any colors in here. Down here we have more amide containing molecules. This is formamide, this is N-methyl formamide, this is DMF, this is N-methyl form analyte. So in this manner you can color different patterns in a molecule. Next I am gonna be talking about substructure search. Highlighting a molecule is also kind of substructure search, but this is kind of more explicit. Here again the first step is grabbing the pattern. It's the same pattern, amide bond here, which we wanna capture. Now in this piece of code, what I'm doing here is I'm running a kind of for loop, and it will screen this pattern over here in each molecule in our data set, and if this pattern is found in our molecule, it will be stored as a list in a variable called matches. So let's run this. Now let's have a look at the length of this variable. So it has 21 elements or 21 molecular objects in this. So out of 50 there are 21 molecules which have this amide functionality. If you want to have a look at this variable, again these are this is a list of all the molecular objects which has this pattern. So what I'm gonna do here is I'm just gonna print the data points which have the molecules with our amide pattern. So let me run this. Now this is the data set which just has our molecules with the amide pattern. Now if you just want to visualize these molecules, I'm just running mol to grid image, which would print out the molecular structures in the form of a grid. So in here you can see all of these molecules have this amide functionality. In this manner you can do substructure search for a particular pattern in a data frame. I'm gonna be ending this tutorial right here, and in the next lecture I'm gonna be talking about how you can delete and replace patterns in a molecule. Along with that, I'm also be talking about fragmentation approach. You can use this Briggs algorithm to fragment a molecule into different fragments, and not only that, you can also join different fragments into different molecules. Also we'll be seeing how we can generate fingerprints in RDKit. And after generating these fingerprints, you can use similarity maps function for mapping different molecules. We are also going to be talking about Tanimoto similarity, and We are also going to be generating 2D and 3D descriptors with the help of RDKit. So stay tuned for the next video. Thank you for watching.